Thank you. If you can sit just under your photo, it will be more easy to find you. Welcome, everyone. Last year, you talked about a bit about your technology and what you do, and this year it's what is the panorama worldwide about the quantum computing, but also in France and in Europe. I can start with maybe Theo or Maud. You both target the creation of fault-tolerant quantum computers, which raise our long-term goal. What are the intermediate steps to do so that can either prove you are on the right track or deliver some business value?
Okay.
Go first.
So before telling you about the milestones, maybe just a reminder, we are at Sequence, and Sequence is aiming at building a quantum computer based on silicon. Why silicon? Obviously, silicon was key to enable large-scale classical computing, and the question the potential, if we were able to do the same with quantum computing, we know for sure that we would be able to scale. We would have excellent qubits in terms of scaling. They're fast, they're small, they've got high quality. And last but not least, we would be able to design low power circuits to control them and implement complex algorithms. So that's the potential. You all have 50 billion transistors in your pockets. In your cell phones, but the problem is that that's not that easy. Transistors and qubits are different, and we've got to find the right path. So to answer Fanny's question, what are the actual steps towards the large-scale quantum computing with silicon? Well, first, it's to build a qubit out of industrial technology, because we know that these ones can scale. And this is what we have done in 2016. We've done a first worldwide demonstration that we can do a silicon out of FDSOI, which is a European technology. And now the next steps is to co-integrate these transistors with the control electronics so that we start demonstrating the potential. So next step is going to be the co-integration of qubits and electronics, and then make logical qubits out of our physical qubits, so that we actually demonstrate the potential of silicon.
Theo?
Yeah, so hi everyone, I'm Theo Pirona, I'm CEO co-founder of Alice & Bob. At Alice & Bob, we're taking somewhat of a different route from Sequence. In the sense that we're not focused on scaling at the moment. We're building on superconducting qubits, so one of the most used platform out there. But we come in with a new architecture of qubit that are meant by design to correct part of the errors, namely the bit flips, if we want to be a bit more technical. But the mindset we're on at Alice & Bob is really that there is no cheating nature. If you want an exponential speed up, you need a machine that is properly quantum, that escape decoherence in some sense. And so for us, the first milestone is really to build that first logical qubit. So far, we've demonstrated that we're able to suppress exponentially half of the errors, basically the bit flips. We still have to demonstrate that we can correct the phase flip, and we're hoping to do so very soon, early 2024, if everything goes according to plan. And from there, once you have a logical qubit, a device that escapes decoherence, that has no causal link with the rest of your classical world, then it becomes a matter of scaling. And actually, you still have one final step that is not often discussed about, which is how you're going to make it universal, because nature's put us a last roadblock along the way, which is that you cannot have a set of universal gates that is compatible natively with a local quantum error correction code. So you have to do some workarounds, and that's going to be the final challenge before just being about scaling.
Thank you. Xavier, maybe do you want to comment, and do you introduce IQM? It's not a French startup, it's a European one.
Yes, IQM headquarters are based in Finland, in Espoo near Helsinki, and we are looking after designing and building quantum computers based on superconducting qubits, but we are clearly in the NISQ regime, so we are not looking at fault tolerance. So we have a very different, I would say, time scale compared to Sequence or Alice and Bob, where we think that even with the technology today, we can still try to reach some advantage. And to do that, we are working on superconducting qubits, and we know that the problem at the moment, it's not that much the scalability issue. For sure, scalability will come in the future, but now the limit is more on the quality of the qubit, on the fidelity of the qubit, and this is where we are putting more efforts today.
Thank you. Olivier, how do France quantum hardware startup fare compared to the rest of the world?
Fairly well. Well, it's a very competitive market. We have to know that. I mean, each of those three folks here, they have competitors. She's competing with Intel, at least. Quantum Motion in the UK is competing with a small company called IBM, at least. Google, to some extent, even though Google is not a commercial vendor in quantum computing. And Theo, well, you have Norquantic, you have Amazon, potentially. And what's interesting in that field is the sheer diversity of technology path and even also technology strategy, I would say. Even if you take silicon qubit or superconducting qubit, or you take the bosonic qubit, like the ones from Alice and Bob, each and every player has a different technology approach. The bosonic qubit from Norquantic in Canada are entirely very different from the ones from Alice and Bob. Intel is not that far from what you plan to do, but there are some differences. So then the difference may come from the backbone research that is connected to the startup. So you have INRIA, you have École des Mines, I forgot probably CEA as well. You have CEA, CNRS, you guys, they have Alto and VTT in Finland. So the backbone research is very important to put that in place. The other thing in the approach is how do you manage a very complicated system, because a quantum computer is not just a chipset with qubits. You have all the stuff around. So you have control electronics, you have cryogenics, you have cabling, you have connectors, you have software, error correction code, you have classical computing, and sometimes you have I/O problems. I/O mean interfaces between the classical computer and the quantum computer, and you need to have a system approach to do that. And as far as I know, for these three guys here and others from France, they hired the right people to adopt this technology integration approach on top of the key physics things to do with the qubits. It's a small answer.
Thank you, Olivier. I appreciate
We could talk
that.
about Candela, Candela, Pascal, and Crystal Quantum, who's not as known.
We have six hardware
companies. So it's the largest number of hardware companies in Europe for one country. Neil said it was the same in the US. I'm not sure about it, but at least in Europe, yes, we have the best diversity. And interestingly, each of the three other players have their own specifics. I mean, Candela, they just talked before. Pascal, we heard about them. They're competing with QRR in the US from Michal Lukin in Harvard. And Crystal Quantum Computing is very interesting because they want to do trapped ions, but with a very different approach that comes out of many different labs in Europe, which is using Rydberg states. So it's a very different approach with trapped ions, which is original. So that's interesting.
Okay, thank you, Olivier. Theo, Mo, Xavier, what is your roadmap and how are you following it? Theo?
Yeah, so as I mentioned before, the goal for us is really to escape decoherence. So at the moment, what we're doing is that we're both working on the basic component, the physical qubit. We're one of the very few companies that still innovates when it comes to basically the microarchitecture of the qubit itself. and we'll be releasing 2 new concept cats, as I like to call them, early in July to illustrate kind of those kind of innovation. At the same time, we're scaling the system size, because even if we're not targeting the medium-sized qubit system at the moment, to demonstrate the full capabilities of error correction and universal gate set, we still need to reach several tens of qubits. At the moment, we revealed at the APS March meeting last March our 4-qubit device, the core component of the error detection system, and we'll soon scale to 6 and 14 qubit to demonstrate proper exponential suppression of both errors at the same time. And from there, well, there is still a long road to go. The target one should have in mind is that the actual proven use cases that have an industrial impact, basically the order of magnitude is 10,000 logical qubit. So we still have quite a long road to go, but we're going down that proven path of fault-tolerant use cases where we know what is the guaranteed speed up.
Xavier?
Yes, regarding our roadmap, what I can say is at the moment we are delivering a 20-qubit system to our partner VTT, the research center in Finland. The system is in acceptance at the moment, and we are committed to deliver a 54-qubit to them next year. So this is in our roadmap. And if we look at a little bit further in the roadmap, we have a 128-qubit in 2 years, so in 2025. But what is more important than just the number of qubits is really about the fidelity. At the moment, we are something close to the 3/9 in terms of single gate qubit, and we are approaching that for the 2-qubit gates. But we know that if we want to achieve something useful with more than 100 qubit, we need to go one step further and reach the 4/9, so 99.99% of fidelity for single and 2-qubit gates. So this is what we have in our roadmap for the next 2 years. And in parallel of this roadmap, we are also working on some specific designs of chips. This is what we call the core design. So we start from the application and we look from this application, the constraint of the application, and how it can be addressed by changing the topology of the chip, changing maybe the compute elements on the chip, and maybe change the programming paradigm of the chip. So not only doing digital gate-based programming on square lattice grids with qubits, but using something different. And we know that by developing, we have the full control of the design and the production of our chips. We have our own clean room, our own foundry. So we are able to work on specific design. And this is also an important path for the next 2 years.
And Maud?
As Olivier said, what we're fabricating is systems. We're looking for a lot of high-quality, good qubits that we've got to control to implement complex algorithms. So this is the way our roadmap is built. We are building on modular approaches that we know we're going to need in the future. And so first thing is that in 2 years from now, end of 2025, we're going to release our simulators and the first generation of qubit chips, where you're going to be able to experiment the quality of the qubits and extrapolate what you can do thanks to the model. And then there is something that is very unique to silicon, is that we're able to design multi-core chips the same way we do with our classical processors. And these multi-cores, they can be used for exponential suppression, exponential mitigation of the errors. And we are going to design in 2027, a first concept of multi-core based on silicon, where we can get used to use the multi-core concept. And by adding that on top, we are developing quantum links so that we're able at the end of the day to deliver a large-scale quantum computer with multi-cores and quantum links between the cores.
Thank you. I have another question. It's about the cloud. What is the role of the cloud in your development? For both of you, I think there is a project of emulators. And how IQM also plays its strategy about that?
The cloud strategy has come pretty late in our global strategy. We have really started to work on premises system because we believe that this is where we could get most of the value and most of the margin. But for sure, now the cloud strategy is really important. So we are working on developing an emulator, not only the emulator to do digital programming, but also an emulator at lowest level to do pulse level access, because we know that, especially if we want to work on the quality of the qubit, this is not only a matter of producing the best chips, but also to control them. So the control electronics is no longer just sending pulses, but shaping the pulses, thinking them differently, putting algorithms into the control electronics. So there is a huge work there, and the emulator should help us designing those algorithms. What I can say is we have the plan to put by the end of the year to give a remote access to our systems. Hopefully, it will be a cloud access. I make a slight difference between a remote access and a cloud access in terms of automation, of automatic provisioning and chargeback. But more or less, this is the goal.
Theo?
Yeah, so for us, the cloud is, I mean, the main purpose why we're currently working on putting our first CAD qubit, building the infrastructure, and then put our first logical qubit in the cloud is really twofold. The first one is to educate. We're coming with a quite more exotic approach of fault tolerance by design and all that new paradigm of bias noise. There's a lot of education to be done around our roadmap and the rationale behind it. But the actual target is to back our claims. When you arrive with the ambition to claim the first logical qubit, the first device to escape decoherence, well, we're going to do a lovely scientific paper. This will convince researchers, but for the general audience, they need to feel it. They have to. We have to back it with an actual device on which you can play. Otherwise, we're just fueling the hype, and I think there is way enough of that in this industry at the moment. Later on, it will be for our industrial partners to develop algorithm and get access to that. But the main purpose is really to showcase the performances of our technology.
And Maud? Is it a bit early for you to talk about that?
No, it's vital. And as Xavier was saying, maybe in the first place, we're talking about remote access, providing remote access to our qubits. And this is definitely very important because quantum computing is hard, and building machines with millions of qubits doing quantum error correction is hard. And we need an ecosystem. And first thing is that we want people to be exposed to our qubits so that they learn to use it and they see it's real and they start, we grow the community and there are more and more algorithms to use them. So that's one fold, is really build an ecosystem, enable the community. And I've done technology transfer in the past, and I've done technology transfer that were very powerful. And maybe at one point we missed enabling the community and we missed opportunities. And this is really important to have our ecosystem that moves at the same pace as the technology is moving. So we need to enable the software ecosystem. That's on one hand. And on the other hand, of course, it's to showcase the technology, convince the investors, convince the end users that it's going to happen.
What can customers can do with a small processor? Just shortly, do you have examples?
Which kind of answer do you want? To be blunt, I mean, and this is not going to please my friend at Pascal, but today there is no machine that can really back a claim of a quantum advantage over a classical state-of-the-art system. And I believe there is still quite a long road. Now, that being said, when you look at the path for industrial customers to really upskill their team, develop their use cases, prioritize and build the in-house expertise and the full-fledged expertise to seize the first mover advantage as soon as the device is there, they need to get ready now. And for that, they need training devices, they need to get acquainted with the pipeline, how to connect, how to integrate, and how to program those devices. So when we work with industrial customers on advising them on prioritizing their use cases, putting the numbers, informing their quantum-ready roadmap, basically, we also provide them with how to connect, how to program, and how to get quantum ready, not only on our platform, but on everyone else, let's say, digital quantum computer platform.
Maud, do you want to comment?
Well, thank you for saying it, Theo. This is not. It would be lying to say that we can solve useful problems with a small number of qubits. Nonetheless, as Theo was saying, if you wait and see that quantum computing is ready, it might not solve your problems. So it's very important that we we co-developed, we are aware of the problems that you're facing, that you cannot solve. And we've got ideas. I mean, there are use cases that have been identified, but now to take these use cases and translate it to actual impact on your industry, well, we need to develop to co-develop early on, and your constraints have an impact on the hardware, and this is really important that we interconnect and keep us posted of how we move on so that we've got an impact as soon as it works, and so that it does not take an additional 3 to 4 years afterwards when the machines are ready. And maybe if they are ready without the end users, they even won't be programmable. So this is really a co-development, and this is the way. Anyway, this is the way innovation works now. There are back and forth between users and providers.
Olivier, you co-founded the QE with the idea to care about the energetic of quantum computers. Do you think that at some point low power consumption will become a competitive advantage to some players, about France players?
Yeah, I think so. So you may remember, for those who were at the Eiffel Tower last year, Alexia Ofev did a presentation, which was a kind of scientific layout of the issues that we are talking about. So could we have either a problem with large-scale computing, with too many qubits, too many electronics, too many cryostats consuming too much power, or likewise, could we find a way where those systems could consume much less power than existing super computing system? So meanwhile, in August, we launched formally this initiative. So we have an ecosystem with about 300 participants. We have 29 symbolic partners, I would say, including the 3 of you and others from who are in the room, C12, which I didn't mention, Pascal and Candela. And we launched our first workshop in November in Singapore with all these people. And what's interesting in the approach, I will explain the approach and then answer your question. What's interesting in the approach is we found out that looking at the optimization of those systems with an eye on the energetics and even the environmental footprint brings a lot of new innovative ideas. It's a kind of orthogonal approach. You have the traditional qubit, error codes, and so that's the classical way. If you look transversally on the energetics, you find ways, interesting ways. For example, the way even the qubit works on the energetic side can have a side effect on how you optimize your code. So these are very interesting things to do. We think that Europe could lead in that space, definitively. We think that if Europe works well together, and when I mean Europe is you guys, you the the qubit developers, I would say, the software developers in the room, Air Liquide with Cryostar, or Blue Force, who's still European as far as I know. We have also electronics, Guillaume, Giovanni, Di Giovanni is over there from Victor. We have other companies doing electronics in the Netherlands, in Germany, in Sweden. So there's a very significant ecosystem in Europe for both qubit design, enabling technology and software. And if all these people work well together, we can build a competitive advantage not only on computing, but also on the environmental footprint. And I don't lessen you with telling that it's going to be important in the future, particularly when you launch a new technology, you can't escape that. I mean, you probably have heard about what the Bitcoin is doing on energetic footprints, the huge amounts of energy it's sucking out of the US, for example, in some places. You have the same problem with AI. We all learn about the so-called LLMs, large language models, which consume a lot of energy to be trained and also to be run. So we know it's a problem for new technologies, and if the quantum industry is able to look at this issue early on in the design phases and the technology development phase, I think it's going to be a very good message to convey to politicians, to investors, that we are acting together in a responsible way.
Thank you, Olivier. I think it's time to conclude this panel. I have so many other questions, and I think in the room also they have questions. And I propose to continue during the cocktail at the end of the day or during the lunch, if you are here, to discuss with them. Thank you very much, all of you. It was really interesting.